Conrad.
Okay, so the first thing I want to address is actually a point that I should have mentioned earlier, but I was kind of glossing over it. We never really established where the zeta function of a positive definite quadratic form actually converges. So let's clear that up. Okay, so if we have a positive definite quadratic form, we'll call it Q of x, in dimension k, means it has k variables. Right. Where does the series actually converge? If I sum over all points in the integral lattice, so where does this converge? For which s? Typically for a Dirichlet series, you're looking for there's going to be some right half plane. And so, so I want to pin down exactly where this happens, or rather, we'll just talk about where it converges absolutely. So this series converges absolutely, which would justify manipulations, rearranging terms, and all that kind of stuff, exactly when the real part of S is bigger than k over 2, okay, and not any smaller, okay. So that's the half plane of convergence. It depends on the dimension k of the quadratic form. So for instance, if you had a binary quadratic form, which was the kind of classical case that people were interested in, it looks like the Riemann zeta function. This converges absolutely. If you take k equal to 2, you get the half plane real part greater than 1, which is just like the case of the Riemann zeta function. Yeah. So where does this come from? How do you show something like this? So the idea is that, as I had mentioned earlier, a positive definite quadratic form, basically, they all look like the norms of vectors or the square roots of norms of vectors. So I had said that we can always write a positive definite quadratic form as the squared length of mx for some invertible matrix. Right? The classical positive definite quadratic form is just straight sum of squares, which is the length squared on Euclidean space. But the general positive definite quadratic form will be the length squared of mx for some invertible k by k matrix M. K by k symmetric matrix M. The place where that comes from, let me just remind you, is that to start off, we can always write positive definite quadratic form in this way for a symmetric matrix A, a unique symmetric matrix A, and being positive definite turns out to imply that A is m squared for a symmetric matrix M. You use the spectral theorem to get that, but then that shows you that x dot ax is x dot m squared x, and you can always move a matrix to the other side of the dot product by using its transpose. So you can move the first m over to the other side with the transpose, but m is symmetric, so you get mx dot mx. Okay, so you get the length of mx squared. Let's just move all this. Let's move all this over a little bit. Okay, so length squared. Okay, so all positive quadratic forms look like length squared, but you might have to apply an invertible matrix first, and then you get them to look like that. So the point is that using the quadratic form, we get a vector space, or using, I guess, the square root. So so this lets us, you know what? Actually, since I just wrote it like that, so now here's what so besides the ordinary length, the function mx, the length of mx, like length itself, is a norm on Rn. I mean, in the sense of linear algebra. Excuse me, a norm on Rk. What's a norm? A norm is supposed to be something we'll call it n of x, which is going to take non-negative values so that it satisfies the triangle inequality and what else? Scalars should come out by their magnitude. Just think about properties of the length function. I'm sorry, I didn't mean it's additive. I meant it satisfies the triangle inequality, and I guess I meant that it vanishes is greater than or equal to 0 with equality. This really should have been the first condition. It's like when you define a metric space. You don't wait to say when the metric is 0. It goes first. But anyway, with equality, if and only if x is 0. So the point is, ordinary length has these features. And if you hit vector by a fixed invertible matrix and then take the length, then you also have a norm. So example could be n of x is the length of x, or n of x is the length of mx for some fixed invertible matrix. Okay. And the point is, so from a quadratic form, if you take the square root of the values of a quadratic form, you're talking about the length of mx for some m, you have a norm, which may not be the usual notion of length, but it's some kind of slightly deformed version. And the key point, this is really, really important, is that in Euclidean space, all norms can be bounded in terms of, any two norms can be bounded in terms of each other by a constant multiple. All right, for any two norms on Rk, each bounds the other up to a constant factor. So maybe one norm is systematically less than or equal to twice the other, and you can reverse it and say the second norm is less than or equal to a third of the other, or something like that. So for any two norms, each bounds the other up to a constant factor. So what this means is, in our case, so for a quadratic form, you can always write it like that, length squared after applying an invertible matrix. We can compare this version of length with the usual version of length for some constants, C1 and C2, that depend on the particular quadratic form. All right, so this is an aspect of either the completeness of the real numbers or the local compactness of Euclidean space. This, by the way, this is also true in a certain sense for finite dimensional p-adic vector spaces, norms. They are defined in a similar way. Also, any two of them can be related to each other. They basically define the same notion of convergence. Any two norms on Rk, if you use them to define a metric by the norm of the difference of two vectors, the topology you get on Rk is the same. Okay, so there's nothing special about the standard basis of Rk in any event. So what's the point here? Well, what this means then is if I square everything, look at the squared length, then on the inside I get the quadratic form itself. And so if we reciprocate, then the reciprocal of the values of your quadratic form, of course, for non-zero x, the reciprocal can be compared above and below to 1 over the, let me just write it in the same way and top and, so I can compare, oh, what happened there? I'm sorry, error. I meant to say c2 squared, right? You decrease the reciprocal by increasing the denominator, increase it up to c2 squared norm, ordinary squared length. And so if I now want to sum powers of 1 over q of x, which is exactly what the zeta function is, I can compare it for real exponents from above and below by these bounds, which up to constant factors look basically the same as ordinary squared length. Okay, so for any for any positive number s, frankly, for any number s, it doesn't be positive, for any, well, yeah, okay, let's take it positive. For any s greater than 0 raised to the s power. Sth power, right? So so we get a constant times squared length to the s, and bounded below by a constant times squared length to the s. So now if I sum everything in sight over the integral lattice zk, so if I let v run over the usual integral lattice, then if I'm summing positive things, I'm summing the non-zero ordinary integral vectors qv to the s. I can bound this from above up to a constant factor, 1 over ordinary squared length to the 2s, and from below, summing up to a constant factor, ordinary squared length to the s. So I have exactly the same thing. On up to a constant factor, I'm summing exactly the same thing above and below. So everything reduces to what's the story if I sum the reciprocal squared lengths, if I sum the reciprocal lengths to a fixed power over the integral lattice, where does that converge? So it turns out that depending on the dimension, if you sum over all the integral vectors, excluding 0, 1 over length to some power a, you can show for real number a, that this thing converges, this is a sum of positive numbers, this thing converges necessarily absolutely if and only if a exceeds the dimension. For instance, take k equal 1. Right? This is basically saying the zeta function converges when the exponent is bigger than 1. Yeah? And so with our quadratic form raised to a power s, taking the exponent to be real, we were relating it above and below to summing the reciprocal length squared. So the sum of the reciprocal lengths to the 2s will converges for s greater than 0 if and only if the exponent 2s is bigger than k. So as s is bigger than k halves. So that's where you get that from. Absolute convergence, you took the absolute values. If s were complex, you take the absolute values, you replace s by the real part of s. So you would get convergence for the real part of S greater than k over 2. So anywhere earlier where I was talking about take the real part sufficiently large so the zeta function as a series converges, this is what I should have been saying all along. Okay. So of course this is not obvious what I was saying. Where was it here? Right. So you can show, right, this thing here. Where does this come from? So I'll put that in the notes. Anyway, so this is a nice, curious fact worth just being aware of. You know, when does the reciprocal lattice power sums over the integral lattice excluding 0? Where does that converge? We know exactly where it happens. You know, at a equals k doesn't work. Less than k, of course, won't also work either. Anyway, all right. So that's really the story on where the zeta function converges initially. And everything else, you have to do some process of, you know, getting the analytic continuation by some method. Yeah. Okay. Any questions about? Okay. So all right. So let's address a question that someone asked. You know, what use can you make of these zeta functions of quadratic forms? So for instance, we know from lecture 3 that these zeta functions have analytic continuation to C. Analytic continuation to C, except for simple poles at two numbers at 0 and k halves. And there's some equation connecting the zeta function for the quadratic form Q and the zeta function for the other one, Q star, which has the inverse matrix to the one that defined A, the one that defined Q. So, so what? All right. Well, so on the one hand, it's just like a toy example. It resembles the Riemann zeta function, right? It starts off as a series. You have a continuation. You have some kind of functional equation. And it very interestingly breaks the Riemann hypothesis. So it just goes to show that the ordinary for the Riemann zeta function, you can't expect to derive the to prove the Riemann hypothesis just by using properties of the zeta function that are shared by these other zeta functions, because for these you have specific examples where the Riemann hypothesis demonstrably fails. So the typical thing people say is, these things typically don't have Euler products, so that somehow should show up in some essential way. In any case, but that's the kind of use of these as just a comparison with the Riemann zeta function. But what other things can you do with this? So you can actually use these. You can use this property, the fact that I can make the continuation and get that functional equation relating values at s and k halves minus s. You can actually use this to prove for all number fields k that there's a notion of the zeta function of a number field. It's defined as, I'm just going to write your sum over the non-zero ideals, 1 over some notion of the norm of an ideal to a power. I'm not going to define the notation here, but there's something that generalizes the Riemann zeta function for every single number field. When k is the rationals, this is the Riemann zeta function. So you can use this to prove for all number fields that that the zeta function of the number field has an analytic continuation to C except for a pole at s equals 1. And there's a functional equation that relates the values at s and 1 minus s. And unlike the zeta functions of these quadratic forms, we expect that all of these guys are going to satisfy a generalized Riemann hypothesis. All right. So as a reference for this, so this is just showing you that even though the zeta function of the quadratic forms might first seem like something maybe I don't have a direct interest, but you can bootstrap the property of the analytic continuation and a kind of functional equation for those guys to derive from that this case for all number fields. And as a reference, if you look in section, let's see, what was it, 1.4.3, in Audrey Terrace's book called, what is it, Harmonic Analysis on Symmetric Spaces. Okay, so this is not the usual method that one sees for deriving the analytic continuation of these things, but it's an example of using these, harmonic analysis on symmetric spaces. At least the second edition. I didn't check if it's the same section in the first edition or if it even is in the first edition. Okay. All right. So that just is to address the question from the audience last time about, is there anything I can do with these things? So here's an example of something you can do with these things. What I want to focus on for the rest of the lecture is to place the zeta functions, the theta functions of the quadratic forms into the setting of modular forms, and show you a few things that you can obtain from that viewpoint. Okay, so right. So the key takeaway is that theta functions of quadratic forms, theta series are modular forms. In a sense, if you were to study modular forms, you initially are shown examples of things that you never would have cared about before, but these things really historically came first. That these, from the quadratic forms, they're generating functions with these theta series, and they had all kinds of curious identities. And eventually, it was recognized that there's this developed the subject of modular forms, and the theta functions naturally fit in there. And so if you understand spaces of modular forms very well, you can get out some interesting properties of the quadratic forms by the fact that their theta series are inside these spaces that people have developed a lot of techniques to understand. So let me explain what a modular form is. Has this been presented in any of the lectures yet? Right. Yeah. So right. So I'll first just to some notation here, right? So we have the group SL2R. These are the matrices. These are the real matrices with with real entries and determinant 1. And then inside of it is the subgroup SL2Z, which are the integer matrices with determinant 1, 2 by 2. Of course, you can always extend this to higher dimension, but we're not going to worry about that. Okay, and so the relation of SL2Z to SL2R, kind of like Z inside of R, is sort of like non-abelian analog. Anyway, there are all kinds of interesting properties of these groups, in particular SL2R. So every matrix in SL2R acts on the upper half plane. Right, the complex numbers with positive imaginary part by linear fractional transformations, where if you've taken a course in complex analysis, you've seen this maybe in the setting of, they're called Mobius transformations. You can even allow A, B, C, and D to be complex numbers. But if they're real numbers with determinant 1, then these matrices, this formula takes a point in the upper half plane, spits out something that's also in the upper half plane. All you really need for this is that the determinant of the matrix is positive, not that it's specifically 1. But the fact that it has determinant 1, these things have very close connections to hyperbolic geometry that we're not going to get into here. We're going to focus on the subset of integer matrices. And the key thing is that this is again, right, this is again in the upper half plane, if tau is in the upper half plane. Second definition? Yeah. Well, what I said is actually correct. Everything I said is actually correct. We're going to focus on, so in fact, let me show you. Here, this was an exercise in my first problem set when I took complex analysis. If you look at the imaginary part of A tau plus B over C tau plus D, where A, B, C, and D are real numbers, it's the absolute value, it's, excuse me, it's AD minus BC times the imaginary part of tau over the absolute value of C tau plus D squared. So if the determinant of your matrix is a real matrix with a positive determinant, then if the imaginary part of tau is positive, then the imaginary part of A tau plus B over C tau plus D is also positive. This is why it brings the upper half plane to itself. So I did really mean SL2R, but we're going to focus on just the matrices in SL2Z. So yeah, I was taking complex analysis. This was a calculation, this equation at the end. I remember thinking, like, what a weird formula that is. But I mean, this is the start of an enormous story related to modular forms and other things. And Shimura was teaching the class, and so in retrospect, to me, it's like, oh, of course he's going to put that on his first problem set. Anyway, yeah. So right. So we're going to focus on matrices that are in SL2Z, not the more general SL2R. Okay. So right. So let me just tell you. All right. So a modular form of weight k. K is an integer parameter for the group SL2Z. We're going to have a function on the upper half plane. Whoops, sorry about that. Function on the upper half plane to the complex numbers such that it's analytic. And here's the key equation. Its effect under changing tau to A tau plus B over C tau plus D is to affect the value by the kth power. And this is supposed to hold for all matrices in SL2Z. I do mean SL2Z in this case, for sure. And as the imaginary part of tau gets large, people often write this as tau approaches I infinity. We think of it as a point goes very high up. It doesn't have to go high up like in a straight direction, kind of meander around, but as long as the imaginary part grows, the value of the function is bounded. All right. So that's what a modular form is. Now, if two functions f and g both fit all of these conditions, then their sum does, any constant multiple does. It's not all obvious what any, oh, I'm sorry, here's an example. Okay, for example, you could take f to be the zero function. All right, so our theory is not empty, but it doesn't tell us very much. All right, so we will see, as I said, theta functions of quadratic forms are essentially modular forms, not quite for SL2Z, but for finite index subgroups, so nearly behave like this. But in any case, so let me just show you a few things, what this condition 2 says. If the matrix is 1, 1, 0, 1, or if the matrix is 0, minus 1, 1, 0, these really do have determinant 1. Or if the matrix is the negative identity. Okay, these are all integer matrices with the determinant 1. So the first choice, the denominator is C tau plus D is just the number 1. And the numerator is tau plus 1. That's the left side. The left side for the second case is minus 1 over tau. The left side for the third case is actually just tau. The minus signs cancel out. When B and C are both 0, everything simplifies. What is the right side? On the right side, when C is 0 and D is 1, that factor is just 1, so I just get that. And when C is 1 and D is 0, I get tau to the k. And when C is 0 and D is minus 1, I get minus 1 to the k. So these are interesting properties. The first is telling us that if you shift tau to the right by 1 unit, the value repeats. So the function is already defined everywhere by its behavior, say, in the strip with imaginary part between plus or minus a half, a strip of width 1. Its values are determined everywhere. The second condition, it's hard to see what exactly that means. The third condition, the third example, would immediately tell us that f has to be exactly 0 if k is odd. Right? Because f is minus f is 0. So we go reduce to the example that I've given you. That's the only example. So modular forms of odd weight for SL2Z, we say, don't exist. I mean, there aren't any interesting examples. You can have modular forms of odd weight, but not for the whole group SL2Z. Right? For subgroups of SL2Z, a finite index, you can definitely have modular forms of odd weight. But for this story that I'm describing here, they don't seem to exist because of this calculation I just made. Anyway, so it turns out that this second condition, if it's true for a matrix A, B, C, D, and for another matrix A prime, B prime, C prime, D prime, that is also true for their product. And it turns out that these first two matrices I wrote in the example here, 1, 1, 0, 1, 0, minus 1, 1, 0, actually generate all of SL2Z. So these equations I put in the box, those two equations, if they're true, then you get condition 2 for all of SL2Z, for all matrices in SL2Z. So condition 2 really reduces to these two properties in the box. Anyway, so let me give you a more interesting example here. So if we took, so for even k at least 4, we have something called an Eisenstein series. So this is actually a better reason why Eisenstein was important in math than that irreducibility criterion. I remember thinking, like, Gauss thinks Eisenstein was like on par with Newton, and all I knew about him was he proved an irreducibility test. I'm like, what? All right. Anyway, Eisenstein series, gk of tau, because G is the first letter of Eisenstein. His first name. Look it up. Anyway, so it's defined as a kind of a lattice sum. You sum over all integer pairs excluding 0, 0, 1 over m tau plus n to the k. So you see what I mean? It's like it's not something you would ordinarily think about, but this turns out to converge for even converges for odd k greater than or equal to 4, but then it's the 0 function, so it's not interesting. In any event, so these turn out to be examples of modular forms of weight k. There's one example in each weight. So for example, if f has weight k and g has weight L, if you multiply them together, it will fit the definition of a modular form for weight k plus L. So for instance, G4 to the third, E for Eisenstein, G4 to the third power, G6 to the second power, and G12 all have weight 12. Okay, they're all weight 12 modular forms for SL2Z, even though they're defined in different ways, and in any case, it's not obvious that they have any relations to each other. Okay, so there's a standard way to describe modular forms as a series. We have this condition, right? We saw that before. And also, the function e to the 2 pi I tau also has its value at tau plus 1 equal to its value at tau. That's just because of e to the 2 pi I is 1. So it turns out when you have a holomorphic function on the upper half plane that's periodic with period 1, that it must be a power series, well, strictly speaking, the Laurent series. It must be a power series in this basic example, e to the 2 pi I tau. So using the boundedness condition in the definition of a modular form, you can show that there's no negative power terms of, in principle, I should allow a sum over all integers and nth powers of e to the 2 pi I tau, but the third condition in a modular form, that boundedness property, actually kills off any potential negative terms. And so this is called, since we traditionally write e to the 2 pi I tau as q, this series is a way to describe modular forms by an expansion with a sequence of coefficients, and so this is called the q expansion of the modular form. It's a power series in q, and we might compare modular forms to each other by looking at their q expansions. The q expansion encodes within it the periodicity f of tau plus 1 is f of tau. But that second condition that I described in the box is completely obscure and not at all obvious from the mere fact that I can write a modular form as a power series. You cannot describe that second condition in the box in terms of some feature of the coefficients. If you wrote down a random power series, it is not going to be a power series for a modular form. Okay, so this is only coming out of the periodicity condition. The other condition, behavior under minus 1 over tau, is totally opaque from the viewpoint of here is a power series. Is it the power series for a modular form? I don't know, right? It's not at all clear. In any case, so what's the, let me tell you about the power series for the Eisenstein series, and then we'll bring in the connection with the theta functions. So for even k at least 4, the Eisenstein series have an expansion in powers of e to the 2 pi I tau. The constant term a naught is twice the zeta function at k. And then you have a common factor that I'm going to take out of the higher order terms. And then the coefficient is going to be a divisor sum. So here this coefficient sigma k minus 1 of n means summing over the divisors of n the k minus 1th powers. Of course, I always mean the positive divisors. So it's a divisor sum. You're summing over the divisors with a fixed power. Now it turns out that the zeta function at k is nearly equal to 2 pi. The Euler's formula for the zeta function on even numbers involves that coefficient of the sum over n greater than or equal to 1. So if you rescale, well, this is called ek of tau, the rescaled version, where you divide by the constant term to force the constant term to have value 1. If you scale a modular form by a non-zero factor, it'll still be a modular form of that weight. So then you get the coefficient to be 1, and then the overall factor turns out to be a rational number. You get rid of all the irrationalities. 2k over the kth Bernoulli number. And then you have your divisor sum. So, okay, so here, these are the Bernoulli numbers. They show up in the power series for x over e to the x minus 1. It's the exponential generating function of the Bernoulli numbers. Okay, so here's a table of a few values of the Bernoulli numbers. Let's see. Turns out that the odd Bernoulli numbers are 0 except for the B1, so we're not going to worry about that one. So the 0, 2, 4, 6, 8. So what do we got here? We got 1, 1/6, 1 over 42. You can make your hitchhiker joke there. Minus 1 over 30, and 5 over 66. And then minus 1 over 30 again, which is a bit of a surprise. Oh, whoop. I missed something. 1 over 40. Oh, sorry. Let me move these over a little bit. We'll get rid of that. Yeah. So you got minus 1 over 30, 1 over 42, then another minus 1 over. These are the only time two Bernoulli numbers are the same, and so on. Okay, so anyway, so this is, oops, okay. So this rescale thing, I call this the normalized Eisenstein series, so that they all have constant term 1, maybe be a nicer way to write them out, because you made all the coefficients rational. Okay, so so here's the great property of modular forms. So let's let Mk be all the weight k modular forms for SL2Z. I still haven't made a connection to theta series for SL2Z. Big theorem is over the complex numbers, they're vector spaces, they're all finite dimensional. Okay, so let me give you an example of some of the dimensions. This is not at all obvious that the dimensions are finite. You're defining these things by some analytic properties, and you're writing them out as power series with infinitely many coefficients, but the ones of a fixed weight, they all live in, the totality of them is a finite dimensional. So here, let me give you the first few, 0, 2, 4, 6, 8, 10, 12, 14. The dimensions are 1, 0, 1, 1, 1, 1, 2, 1. Let's see, dimension 16, weight 2. Okay. So, for example, I had said before that, for instance, E4 squared and E8 are in the space of modular forms of weight 8. And what's the dimension of that space? According to the table, 1. And so these two things must be scalar multiples of each other, but they all have constant term 1. And so since the dimension is 1, that actually forces E4 squared has to equal E8, which is a bit of a surprise. It's some funky identity connecting the divisor sums for sigma 3, 4 minus 1, with the divisor sums for sigma 7. Or, as another example, right, E4 cubed, E6 squared, and E12 are in the space of modular forms of weight 12. And what's the dimension of that space? 2, which means there's going to be a linear relationship among them, and all you have to do is look at the first few coefficients, treat the constant and linear coefficients as pairs of numbers, and get a linear relation among those three pairs, and that linear relation has to propagate all the way down the line to all coefficients in all degrees. And so it would turn out, for instance, so E12 has to be a linear combination of E4 cubed and E6 squared. And so just by looking at a few coefficients, you can solve for A and B. A turns out to be, let's see, 411 over 691. And B turns out to be 250 over 691. 691 turns out to be a numerator in the 12th Bernoulli number. I left that off the list, 12. Ugh. What do we got here? 691 over 2730 or something like that. 691. So I was at Subway once, and the receipt, $6.91. I was very excited. Usually they ask you, do you want a receipt? It's like, no. Do you want a receipt? Yes. And then I proceeded to lose it. I was so upset with myself. Of course, you're never going to find anything for $6.91 at Subway anymore. Anyway, all right. So what's the link to modular forms? The link to modular forms is that if Q is a k-dimensional integer valued positive definite quadratic form, integer valued, you may have some coefficients in the matrix, you might have halves in them. Anyway, then the theta function for the modular form, the theta function for the quadratic form is a modular form of weight k over 2. So I should have said let k be even. So it's a modular form not of weight k, but of weight k over 2 for a finite index subgroup of SL2Z. I'm not going to define modular forms for finite index subgroups. It's very similar to the definition for all of SL2Z, but there's some additional technical complications for a finite index subgroup of SL2Z. You can pin down and describe the subgroup. I'm not going to do it here. I will say that sometimes that subgroup is all of SL2Z. So to be a modular form for all of SL2Z, there is a restriction. For instance, you do need 8 to divide k. I'm not going to explain where this comes from, but for example, so for instance, it turns out, so let's take k equal 8. If k is 8, then k over 2 is 4. You're welcome. And so what's the dimension of the space of modular forms of weight 4? 1. And so when Q of x is the 8-dimensional sum of squares, its theta function, its theta series, turns out to be in the space of modular forms of weight 4. But the dimension is 1. Oh, I already said the dimension is 1. But the Eisenstein series for weight 4, the normalized Eisenstein series, which turns out to be 1 plus 240 times the sum over n at least 1, sigma 3n, q to the n, this is also in M4. The theta series has constant term 1, right? Because the only way to write 0, the constant term 0, as a value of the quadratic form is one way, with the 0 vector. So that has constant term 1. E4 has constant term 1. And thus, the theta series has to be E4. In other words, for all n big equal to 1, the number of vectors in Z8 which have squared length n is given by 240 times the sum of the divisor sum with summing the divisors cubed. Right? That's not at all obvious, but it's an immediate consequence of being able to recognize that the theta series is in a certain space of modular forms, which happens to be one-dimensional. You already know a construction of something else in that space. They have the same constant term. Since it's one-dimensional, they must match term by term in all powers of Q. And so you can read off this count. This count on the left side, those are the coefficients of the theta series of that quadratic form. Yeah? And the last thing I was going to mention is if we took k equals 16, in weight 16, if you have integer valued quadratic form for weight 16, then this will have weight k over 2 or weight 8, and the dimension of M8 is 1. So the theta series has to be the normalized Eisenstein series because they share the same constant term. And so the representation numbers for that quadratic form have to be the coefficients of the weight 8 Eisenstein series, which turn out to be 480 times sigma 7. Okay, that was the sum. This is the sum of the divisors to the 7th power. Okay, the 480 just turns out to be a common term in all these factors. So remember I had said that John Milner had found 2 examples of quadratic forms that you could not link to each other by an invertible integral change of variables, yet they had the same representation numbers for all n. And this is why, or this is a reason why, that the space of modular forms is just so small that even if you have 2 different constructions of quadratic forms in dimension 16 that are integral valued, it turns out that their theta series are forced to live in this one-dimensional space, and since their constant terms agree, all the coefficients agree in all powers, and so the representation numbers must be the same, and in fact must be given by this formula for all n. Okay, so there's a whole lot more you could say about theta series. If you understand exactly which spaces of modular forms they're in, you can get relations among different theta series. Anyway, so I'm a little over time, so that's a good place to stop.